So now let's look at using simulation to try and determine if a difference in proportions between two populations is significant or not. Just some notation. Now that we've got two populations involved, we just subscript all those variables that we did before. So in population 1, we'll call that the males. We've been using n for sample size, so now we'll just say n sub 1. We had 17 males in this. And our count was usually an x, so we'll call this x sub 1. There was 4 cancer diagnoses. And then our sample proportion was usually a p hat, so p hat sub 1, 4 out of 17, or what did we say? 20. That's about 23.5%. So that's our cancer rate among the males. Let's label that so we remember which is which. So P1 hat is cancer rate from sample of males. And then likewise, population 2, females. We had a sample size of 24, so we'll call that n sub 2. We counted 8 cancer diagnoses, so that's our x sub 2, and our p hat sub 2 is 8 out of 24, or 33.3%. And so p hat 2, don't know if I have enough room to squeeze it in here. That's going to be cancer rate females. OK. So what we're interested in is looking at this difference, right? So right now we have that P1 hat minus P2 hat is 23.5% minus 33.3% for a difference of negative 9.8%. So the question now becomes, is that significant? Could we expect to see that sort of difference if in reality there was no difference in the entire population? So now let's look at how we will do that by simulation. OK, so let's try and simulate a situation where the rates of cancer between our two groups are the same. So remember, here's our situation. Males, we've got 17 males in our sample 4 had cancer, giving us a rate of 23.5%. And then on the females, 24 were sampled and 8 had cancer for a rate of 33.3%. And we ended up with a difference of negative 9.8% between the two, P1 hat minus P2 hat. So for the simulation, what we're going to do is we're going to assume that the rate of cancer, notice that we had 12 cancer and 29 no cancer. So the combined together, 12 out of 41, 29.3%. So what we're going to do is try and simulate that percentage rate of cancer and then just assign it randomly to males and females. So we've got 12 cancer. I'm going to represent those with red cards. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the blue cards will be the no cancer. We need 29 of those. 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 24, 25, 26, 27, 28, 29. So there's our Cancer and no Cancer. And we're going to shuffle those up. The idea is that the chance of males or females of getting a red card is the same because it's this 29.3% chance. All right, so we are going to randomly deal these out to the males and females after I've got them shuffled here. So amongst the males, we had 17 in our sample, so we're going to deal out 17 cards. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then that means there should be 24 left over here for females. Now let's calculate the proportions we got individually. Altogether, remember, it's 29.3% is the rate of cancer. But we've shuffled them up, and because of variation, it's not always going to come out to be that. Let's see. Let's count the cancer here. There's 1, 2, 3, 4, 5. So 5 out of 17. And we don't even really have to count the other deck because we know how many Cancer cards there are total. There's 12. So that means out of these 24, there must be 7. Or as percentages, this is 29.4%. 29.2%. So what we've done here is simulated a situation where the rate of cancer is 29.3% and gender has nothing to do with it, right? Because we just assigned cancer or no cancer randomly to these two groups. So this little fluctuation we're seeing of 29.2 and 29.4, that difference there of 0.2% is purely by random chance, right? And the idea is we'd like to repeat this process over and over again to build up our null distribution, and our null being that there is no difference between these two groups. So let's move over to the applet and try that now. So now let's see how that card dealing that I did plays out on the applet that simulates. So I've chosen the 2 proportion applet here, and you have an option of just putting in summary information, which we could, but the thing I don't like about that is I can't change the labels. So I'm going to use actual data. I've got it here in a spreadsheet, so I'm going to copy those, and I'm going to clear data here and paste in. And now here's all the data, all that sample data that we were looking at. If you want to use this, keep in mind all of these labels have to be a single word. That's why I took out the space here in no cancer and in cancer status. So if you're putting in data, when you label stuff, use a single word. OK, so I'm going to use that data. And here it even makes us a nice segmented bar graph here. We saw that before. Right now it's measuring success as cancer. You could switch that either way. But we were comparing rates of cancer, so that's exactly how we wanted it. Here's our negative 9.8% there. Right now I've got it measuring difference in proportions. There's some other options we'll get to later. There's relative risk, which we saw before, but we're interested in difference in proportions. You can also show the table. There's our 23.5% and our 33.3% in a table there. OK, so now, just like I shuffled out those blue and red cards into 2 groups to simulate just random assignment of cancer or no cancer, that's what the computer is going to do for us. So if we do one shuffle, randomly giving either cancer or no cancer cards to the males and females and calculating the difference in proportions. So far, it's done one shuffle, and it got a difference of 0.125. Unfortunately, this label's a little long. It's pushing that number off there. But notice that our totals are still the same, right? Underneath cancer, we had 12 originally, and there's still 12. And under no cancer, we had 29 originally, and there's still 29. Maybe I can resize this. Oh, there we go. Now you can read it better. This is still shifted over a little, so that's male 6, 11, 17, 6, 18, 24. Okay. So we could go through and shuffle cards, assigning those cancer and no cancer randomly to the males and females. And obviously we want to do a bunch of shuffles. So now we've done about 3,000, 4,000 shuffles. And notice we're getting a distribution similar to what we're used to seeing with single statistics, right? This sort of bell-shaped symmetric distribution. Notice the mean, on average, the difference in proportions is roughly 0, because you wouldn't expect the males to get cancer more or less often if we're just randomly assigning it, right? So we're seeing all of our different shuffles here, but in the long haul, on average, the difference should be 0. Okay, so we want to measure the significance of our statistics. So remember ours was a negative 9.8%. So what is the likelihood of us having got that if there really was no difference in cancer rates? And notice we're getting a p-value here of about 38%, so a pretty large p-value. So it's reasonable to expect to get this sort of difference even if there is no difference in the population. So let's make sure we're clear on the logic of this. We were randomly assigning cancer or no cancer to males and females here. That's what the shuffling's doing. And here we're seeing the possible things that you could get in those random assignments. Just because of random fluctuations, sometimes there'll be more cancer in the males, sometimes more cancer in the females. But in the long run, on average, there shouldn't be much difference. And we're seeing that 0.2% difference at 4,000 shuffles. So what's the likelihood to have gotten the difference we got if cancer, the difference in cancer between males and females is just 0? Well, still fairly likely at a p-value of 38%. So this difference that we're seeing, this 9.8% difference we're seeing in our sample, is not significant. So we would not be willing to conclude that there really is a difference in the whole population.